Welcome to the fundamental theorem of calculus, part 2. So our theorem suppose that f is continuous on the closed interval AB and capital F is an antiderivative of lowercase f. Then we get that the definite integral from a to b of lowercase f of x dx is simply equal to capital F of b minus capital F of a. So for example, if we are asked to evaluate the definite integral from 2 to 5 of x squared minus 3x plus 1 dx, we need to find the antiderivative of x squared minus 3x plus 1. So we need to find an antiderivative. So we can find the integral of x squared minus 3x plus 1 dx first. So this is power rule for antiderivative or for integration. It says we raise the power by 1 and then divide by our new power. So x squared would go to x cubed over 3. Then we'd have minus 3. X would go up to x squared, and then we divide by 2. And then the antiderivative or integral of 1, we get x. And then we have a plus c technically on the end, right? But since we only need an antiderivative, we can go ahead and set c equal to 0. So we'll just set c equal to 0 and take this. So now I'm going to introduce a new notation. This way you don't necessarily have to write out the antiderivative separately. So the new notation I use, the definite integral from 2 to 5 of x squared plus 3x oops, minus 3x plus 1 dx. What I do is I'm going to write the antiderivative we chose. So x cubed over 3 minus 3x squared over 2 plus x. And then I do a vertical line, put a 2 down at the bottom and a 5 up top. So this indicates we've already taken the antiderivative or found an antiderivative. It just remains to evaluate. So now we are going to plug in 5 and 2. So we will do 5 cubed over 3 minus 3 times 5 squared over 2 plus 5. And then we will subtract off, plugging in 2. So we have 2 cubed over 3 minus 3 times 2 squared over 2 plus 2. Then it remains simply to finish the arithmetic. I need to give myself a little more space. Okay, so from here, if we do our evaluation, we're looking at 125 thirds minus 75 halves plus 5. And then we are subtracting off 8 thirds minus 6 plus 2. And we wind up getting 10.5. So that's finding that definite integral. You just needed to find an antiderivative, evaluate it at both bounds, and subtract. So going again, we wish to evaluate definite integral from -2 to 4 of 5e to the x dx. 5e to the x, if we take that integral of 5e to the x dx, the 5 comes along for the ride, and e to the x is our special function. We just get back e to the x plus c. We're going to set c equal to 0. And we have the definite integral from -2 to 4 of 5e to the x dx is equal to, we are going to do 5e to the x, have our vertical line from -2 to 4. Plugging in, this is 5e to the 4th minus 5e to the -2. And that's as simplified as we're going to get in this case. We could technically write this as 5e to the 4th minus 5 over e squared if you want. But this is our definite integral in exact form. One more example. Let's go ahead and evaluate the definite integral from pi over 4 to pi over 2 of 2 cosine x dx. Again, let's go ahead and find the integral of 2 cosine of x dx. Well, that is just 2 sine of x plus c. Again, we'll set c equal to 0. So we have the definite integral from pi over 4 to pi over 2 of 2 cosine of x dx. We are looking at 2 sine of x. And we're going to evaluate that at pi over 4 and pi over 2. So this becomes 2 times sine of pi over 2 minus 2 times sine of pi over 4. And sine of pi over 2 is just 1, so we have 2 and then minus 2 times sine of pi over 4 is √2 over 2. And so we get 2 minus √2. So again, this is evaluating the definite integral. As you can see, this is much, much, much more pleasant than doing Riemann sums and taking the limit as n goes to infinity. So when you evaluate definite integrals, this is what you do unless I specifically ask you to use the Riemann sum.